And we are live. Hello, everyone. My name is Yuri. I hope everyone can hear me just fine. And I thank you for coming. Today we are going to talk about static analysis and how static analyzers are made, and specifically about type system, which we use. So, about me, just I'm a C++ developer at PVS Studio. If you don't know, we are developing a static analyzer for C++ mainly, also for C# and Java. I'm working on the core module. It says here that I also write diagnostic rules, but not anymore. Mainly it's core. And what is this talk about, really? Well, several things. Well, first, if any of you don't know yet, I'll briefly tell you what static analysis is and why it's useful, what it has inside, like kind of how it's built. We are going to focus on the type system for C and C++ because that's the hot topic here in PVS Studio right now. And I'm working on it intensively. And I'll just give you a small comparison of what it used to be and what it's going to be and what, like, the stage it's now. But first, what's a static analyzer, right? I think it's a term which is not so obscure these days, but still, it's not very common. Let's say it like that. Well, static analysis is basically an automated code review, or you can look at it as, well, as some kind of a compiler which doesn't really compile anything, but it makes other useful things happen. So how a compiler is built? We need this to understand the structure of the system. Every compiler these days basically has some parts. First and foremost, it's front end. It's where you feed your source code and you get your syntax and semantics of your program analyzed. And the result of that is a syntax tree. It has usually some kind of intermediate representation. In Clang, it's called IR. And then this thing goes to the middle end, so-called. The middle end module does some platform independent optimizations on your code, on your abstract representation. Then the IR goes further, and then it goes to the backend, which creates assembly code. It does some platform dependent optimizations, and you get an object file which is then linked to an executable or a library. So I think everyone knows this, just a reminder. Now, what's a static analyzer? Basically, it's the same thing, except for code generation and optimization. So again, we still have a front end here, which does mostly the same things the compiler does. And then next, we get, instead of that IR middle end backend thing, we get diagnostic rules which work on your basically on the abstract syntax tree. It has also some mechanisms like data flow to track variable changes throughout the program, but it's not too important right now. So diagnostic rules of a static analyzer are like compilers' warnings, but they can afford to give you more information and complain about things a compiler won't complain about, because the compiler has a job of creating your executable, and diagnosing something which does not affect compilation, it's not really its job, so to speak. Okay, so this was a short intro into what we're dealing with. So let's go back to types, which is the main topic, right? In C++ and C, we have quite a huge number of types and quite a type system, in all honesty. So what do we have? We have built-ins. We have so-called derived types. We have user-defined types also. Built-ins are your ints, floats, a void is also a built-in, null pointer, all this stuff which the compiler just knows about. Then derived types are pointers, arrays, which are just pointers really in disguise, references, they would like to be pointers, but they kind of cannot, and functions, which also boil down to pointers in the end. So derived types are basically pointers for the most part. And user-defined types are structures, classes, unions, and enumerations. I don't mention templates here because templates are just another language within a language. They make your life easier, but they make life of compiler guys a little bit harder, I think. And the best part I love about it is that all the types are interconnected in weird ways sometimes, and they are convertible to each other. So it's quite a complex system. This thing doesn't even start to represent the entire complexity. But anyway, let's say you want to create a C++ or C compiler. I don't know why, but let's say you want to. How would you represent types in your front end in order to correctly determine the way what data at which point of the program is used? Okay, so there are two schools of thought, I guess you can say, on this. There's an old way which I think started it all, is representing types with just encoded strings. So let's look at this declaration here. It's a pointer to a const int. So what we do with it, we just take every part of this type and put it in a string. So it's a pointer, which is the letter P in our system anyway. Const will be applied to whatever is under the pointer, and int is kind of easy. And also we've got this cute character here, which represent a null terminator, of course. Now, the other approach you could take to types is, well, basically this. You just take everything you know about types in your language and you somehow implement the entire scheme with interrelations in your front end. Now, those approaches, they both have advantages and disadvantages. Just a spoiler, it so happens that our analyzer for C++ and C uses the first approach because it's kind of an old code base. Okay, so let's take a quick look at encoded strings. So they, of course, have advantages, and the advantages are they are more cache friendly because your string is always located in memory contiguously. I tried to think about other advantages of this approach, and frankly, I couldn't. I couldn't find any. So I guess that's it. And of course, strings are kind of slow because you have to iterate over them all the time. Algorithms of working with strings and looking something up inside and dealing with characters and so on are quite inefficient. And you might need, and probably you will need, to pass over the same thing multiple times in order to get all your information, all the information you want. Otherwise, you risk losing information, and if you say cut the string into pieces, you risk losing information unless you keep everything memorized, and then again, it's a whole pass over the same thing again. And strings are not, at least in C++, are not the most convenient thing to work with. In C++, it's better than in C, but still. Also, there is one tiny issue if you want to encode everything in a string. So these are comments from our code, from the module which deals with encoding. And as you can see, there are quite a few letters used here, and that's even not the entire thing. And the choice of letters is sometimes questionable. Let's say we have Z for null pointer over there at the right. So why is it Z? Where's the logic? Well, the logic is simple. Z was available. It was free, so it was used. In other words, we are running out of letters, and if you try to encode everything, you will probably run out of letters. Just to give you an example, what you would be dealing with if you had encoded types in your compiler or whatever is this. So let's try to guess what string represent each type here. So for this int pointer, I think it's easy. I think everyone can easily get this. There's a different example when you declare a class. You want to know about this class, of course. You want it to know its type. And if you encode it, you will get something like that. This little group of characters in front of the name, they represent the length of the string which will follow of this substring. Okay, a more elaborate example, I guess. So it's the main function we know and love, and what it looks like. It looks like that. It's kind of, I think, obvious here what everything represents. If we read it left to right, we will read it like that. It's a function which takes int as a parameter, which takes a pointer to const char as the next parameter, and it returns an int. Not the best thing in the world here, because if you want to get the function's return type, or say the second parameter or whatever parameter you want, you will have to traverse the string, or you will have to come up with some caching and stuff like that. And this is an example I really like. It's my favorite one, to be honest. If anyone can guess it, you are genius, but because I had to copy and paste it from a real debugging session, and it goes like that. So there's a lot of stuff going on here, and that stuff is not really obvious. And you really have to understand how this thing is organized to do something with it, which is, well, it's not abstracted well. Okay, those issues with encodings are really minor because you can get used to everything. What is a more serious problem is, as I said at the beginning, is slowness. And the slowness goes from, well, basically the fact that you need to really understand what those words and encodings mean. Here's an example. It's completely synthetic. We have typeinfo, a typeinfo class in our code, which has some interface methods. And in this specific example, let's say we get some type from somewhere, and we want to know if it's a function or not. Let's see what happens. Usually, a check like that is a quick bug out check, so to speak, so you can easily leave if you don't want to run all the further logic, if something is not good for you in this case. So is it a quick bug out check really, as it wants to be? Well, let's see. We'll take a look inside that specific function, and there's a lot of going on here. The actual check whether it's function or not is at the very bottom when you actually check it for letter F, which is, as we saw, is a marker that we are dealing with a function. It's at the start. But the question I usually ask people who see this first, I mean people here in our team, is how many loops do you see in this picture? How many? Well, obviously, the function itself doesn't have a loop. But we have two really suspicious calls here. The first one, I'll talk about it a little bit later. The second one just goes over a string, and it basically skips every const, volatile markers, ellipsis arguments, and so on. So it's a loop. We've got one at least. And the normalized one, the first one, well, it's a pain. So it checks CV qualifiers of your type, and it sets flags for them for later use. It resolves type defs. In your encoding, you may not have this beautiful function signature. You may have something which has been some alias for the type. It also tries to figure out your templates, and if you have a class, it will give you information about that class also. Everything, the results of that function is usually a changed encoding or additional information added to the object itself. Okay, so this one is obviously, it goes over the string. This one goes to the symbol table in the current scope to look up the symbol. This one will just skip because it's too, how to say it, it's too obscure. It does some magic, which doesn't always work. And for classes, you again go and look at the symbol table. Now, what do we have inside of those? This one is obviously a loop. This one probably is just a lookup in the hash map, right? Well, actually not, because it's recursion. Because you may have type defs inside templates and so on, and it uses this thing again. This one is heavy recursion, and it loops back to type defs and usings and stuff like that. This one is also recursion because you may want to figure out all those things first. Okay, so encoded strings for types may not look too bad, but they are too bad, really. Now, so why am I telling you this? Well, because of that. Because if you want to check something, if you want to check if something is a function, it must be simple and quick. And at some point, we decided that we need to come up with a better system. So the better system, how would it look like? At this point, I'll play Captain Obvious and I'll say that it was a brilliant idea. Types in C++ and C are sort of kind of a hierarchy. So, hey, why don't we represent them with a hierarchy of classes and just throw those stupid strings away? And so we did. Here I want to take a moment and just praise Clang, because it was an inspiration for me when I was developing the type system. I didn't copy it exactly, of course, because we have different goals with Clang, but it was really helpful. Its source code is good and the compiler itself is excellent. So thank you. Thank you, Clang. Now, this hierarchy of classes to represent a hierarchy of entities. How it looks, what it looks like. So we've got the base class for type, which represents just any type. And inside it, it has an ID, because we need to understand what we are looking at. We are dealing mostly with a pointer to the base class. So IDs are different for different types. It has canonical type, a so-called canonical type. I'll tell you what it is a little bit later. And all the derived classes which you can produce for different stuff like pointers, references, classes, and so on, they contain specific information. If you take a pointer type, it will have information about the type it's pointing to, so you can easily extract it. Now, remember our code from the beginning with the function check. Well, here's basically the same fragment, but with a new type system. And again, it's a quick bug out check. Or is it? Well, let's see. So the function with many loops and recursions turns into this. You can check multiple types at once, and it just involves checking a single field, basically, in the type class. And this field is a char, essentially. The type itself is kind of small. So that's the idea. I think it's pretty obvious. What may not be obvious is what a canonical type even is. So let's look at this example. We have an int variable, and obviously it's an int, so it's a built-in type, and its canonical type will be also built in. In this case, the type itself and its canonical representation are the same. But things get more interesting when you move to aliases. So let's say you want to create an alias for int and have a variable of that. Type of A will be here this. So the type itself is an alias. It's a type def. We need this information, so we carry it around. And the canonical is what's under the type def. The main reason for having this canonical representation is to avoid dealing with aliases when you don't need to. It also serves different purposes, like for template specializations, but mainly it's for resolving aliases. So what I mean by you won't have to deal with aliases when you don't really need to is, if you take a look at that, you have quite a small alias chain here, but they can grow really long, type defs to type defs and so on. And to figure out the resulting type of A, we need to take a look basically at canonical. So let's take a look at A here, and I'll just show you what it consists of. So it's an alias, it's a using. We also need to know that for different reasons in diagnostic rules. Its canonical type is built-in int, and it may look here like we are losing information that this is an alias to an alias, but no, really, we have a source for the alias in this case. What it helps us do is you can easily extract the underlying type to which all those chains of type defs are pointing to, and also you can walk the chain if you want to. So using the source of the alias, you can just unroll the entire chain if you need to, and yeah, sometimes it's needed. So overall, as I said, we have the base type and derived types, derived classes in our hierarchy. So here we have built-ins. Don't worry, there are not too many of them. Built-ins are complex type from C, pointers, arrays, member pointers. Also references, which are of different kinds. We have R value, L value, and forwarding references. We have classes. We have class member types, because a class member is not just its type, it's also the real thing, the declarator for it. Enums, of course, aliases, functions, and not all functions are born equal. So we have constructors, we have just plain functions, constructors, destructors, operators, of which the assign operator is a unique thing. because it can only happen inside a class. Also cast operators, which are not really operators, but rather conversion functions. Of course, we need a way to represent auto and decal types. We've got templates, template variables, which kind of differ from plain templates. Template parameters get their own type. Template specializations get their own type. Also, for different type conversions, we want to track how did we get to some point. So we've got adjusted types, which are basically types that underwent some changes, some operations on them. Deduced types you get from auto, decayed you get as a result of decaying an array, for example. Template args you get from, of course, substituting template args when instantiating a template. For parameter packs, there is its own type, and you get template instances. Um, it it covers pretty much everything we need right now from our type system. And I don't know if you noticed or not, but I kind of dropped the topic, which is an important one, but I just didn't talk about it. It's the topic of qualifiers. You get all those types. It's great and fine, but what if you write const, or better yet, if you write something like that? So here we have a built-in type, which is an int, but we also have two qualifiers attached to it. And in our type system, we have type IDs, right? So would the solution for representing this thing be something like that? I think it's fear-inducing. At least it scares me when I look at that. So really, no. We are not going to do this scary thing to anyone. So what shall we do? Well, again, that's the idea I borrowed from Clang, and again, that's probably the best thing I borrowed from them. I like this concept very much. The concept is called call type. Call type is a type to which qualifiers are applied, and how it works is interesting. So under the hood, it's just a type pointer. So we can look at it as a pointer. What makes it special is if I asked you how many bytes of address you have on a 64-bit system, what would you answer? Most people, I think, would say 8. We are talking systems like Windows, Linux, Mac, the big three. People who think that we have 8 bytes of address on those systems are kind of right, but at the same time, they're kind of wrong, because you actually don't get to access everything in your address space. In user mode, when you are in your regular application, a pointer contains an address in memory and a byte of zeros. This is because this byte there is reserved for system users. It's not accessible. It's always zeroed out. I think CPUs these days, either they can automatically drop it in user mode, or they are going to be able to do it at some point. So that looks like a waste of space, but really it isn't, because that's what helps us to represent different qualifiers on different types. So basically what we do, we take this byte here, we put an address to the actual type instance, to the 7 bytes we have for address, and in this little 0th byte we just put some bits. So we store const, volatile, and restrict for C there, and we've got 5 spare bits really. So what I'm going to, the way to represent qualifiers for types is not to put them inside types, but rather apply them to a pointer which points to the corresponding type. And it works great because those call types, they behave like pointers. You can copy them around, they're lightweight, they don't cost you anything, and you can store them anywhere you want, and so on and so forth. Yeah, so it's just a pointer again. It has qualifiers, it has a pointer to the base class. Of course, it doesn't store it inside as a pointer, it reinterprets it as a number. But anyway, otherwise, you can just dereference it like a regular pointer. You can use the arrow operator and all that good stuff. Okay, so how does it fit together in the grand scheme of things? We've got our type system, which is actually a factory which produces types. You cannot create a type instance yourself. You have to ask a special class to do that for you. And the reason for that is the cache. Why cache? Because you really don't want to have a lot of instances of, say, int inside your compiler or static analyzer, because they will clutter your memory. And how will you know if they are the same type if you have multiples? You can, of course, compare their IDs and information from within them, but it won't be too efficient. So this factory class, which is called type system, it hashes the types it creates based on what you pass to its functions, which actually make types. So every int will be just a single instance in your application. Every pointer to int will be just a single instance in your application, and so on and so forth. So every function, every class, if they have if they are the same type, you will have only one instance. And just for convenience, because we are passing call types around, you cannot really rely on the types methods. You will lose qualifiers otherwise. The type system provides traits. Traits are like type traits from the standard library. They basically do the same things, but during runtime. Okay, so what profit do we get from it? Types are mutable. Once created, they can be changed, and you cannot break them in any way like that. Types are single instance objects, not singletons, but single instance. There's only one of each. You can compare types really by hash values. it makes your life easier. And those call type pointers, they're not nullable. They have unresolved type, so-called, under the hood. If you default construct them, you can dereference them. Nothing bad is going to happen. Okay, so yes, I guess it's good. Let's see what we have actually inside our type classes. So the base class is really simple. You can ask it for its ID, which is stored here. ID is just an enum with the unsigned char as its underlying type. This one checks for unresolved. We can check if it's some kind of auto and do something about it. You can get its canonical. You can wrap it into qualifiers and produce a qual type like that. And you can know its size and alignment, which are working through type system again. This hash is for the factory. It uses it to identify types by its own means. And basically that's it. So that's the whole base class for the type. And let's take a look also at some derived one. We cannot, unfortunately, go in too much detail about this, but I guess I will just give you an overview. So let's take a look at a pointer type. It's inherited from the base type class, and what information it adds as compared to its base class. You can dereference it, and it stores a call type of the thing it points to with all the qualifiers. And this is just a quality of life feature. You can quickly check what the pointer is pointing to. In this scheme, even though we have a class hierarchy, we decided to go really against polymorphic usage. So no virtual functions there. Let's take a hypothetical function which wants to know if you have a pointer which points to an int. It has a stupid name, but it will do. So the way we would do that with encodings, we would just traverse the string character by character and try to figure out what's what. Here, it becomes quite simple. We just try to cast our type to a pointer. If we fail, we just bug out. If we don't fail, we dereference it, try to get it as a built-in type, and do a check like that. So it's quite simple. It's less verbose than it would be with encodings, and I think it works faster, really. Well, this try-get-as function you saw there is a dynamic cast, which is not a dynamic cast, really. It can cast your type pointer you get from call type based on its ID to the derived class you want. There are two versions of it. It can cast by type you give it or by ID. And this to function there, it just does that basically. So it just utilizes static cast. Otherwise, it's null pointer. Very close to how dynamic cast would work. And this thing here is a set of templates for each type, which mm, correspond types with IDs. I made a cardinal sin here by creating macros, but this is what when you create a new derived class from the base type, this is what you should call and give it the type name and the ID. And remember I talked about traits. There's another way to do the same thing. Again, the same stupid function. You can do it like that. Check if it's pointer, remove pointer, try get as built-in, and go just check if it's an int. And those trait things, they mimic what we have here. This is a screenshot from CP reference, and those are screenshots from our code, really. They just are the same, basically, which we use in our code, and just to deal with call types in the same basically way we would do in our code at compile time if we wanted to use type trace from the standard library. Well, here's just an example of how a trait is implemented. Let's look at decay. If we just check the way decay works, we can code it quite easily. So first remove const volatile and reference from your type. Functions become function pointers, arrays become pointers to underlying elements. Yeah, this way you can manipulate all those things inside your code base. And now the final how it fits together part. So let's say we get this as our input. This piece of code, it goes to the parser. The parser makes an AST. It's a declaration statement, obviously. Then types get determined. Here for a pointer, we get the resulting type as a pointer to int. This wrap there in the first line, it says create a call type which has empty qualifiers because we don't have const or volatile here or anything. This type is assigned to the AST node, which has been created. And this AST node later gets into a diagnostic rule, and here you can use traits to work with it and determine its type. Or you can use different ways, like addressing the type itself. And we are running out of time. So yeah, just as a summary, this was a brief introduction in what we have as a type system, really. And I just don't have time to elaborate really on that. I could talk about it for hours. Maybe if this topic interests someone, I can turn it into a series of talks and give you more information on any specifics we have inside. But in any case, thank you everyone who was listening to me. And I think right now, since we have a little bit of time, I'll see if we got any questions, and then I'll just answer whatever I get. Otherwise, thank you, and that's it. I don't think we have any questions really, unless I'm missing something. Just a quick check. Okay, so no questions. So thank you again, everyone who was listening, and that's it for me. Have a nice day.
Hi everyone, I'm so thrilled to be here at the NDC TechTown. I am Antonio Liccardi, and today I want to share with you a topic very dear to me, which is how to automate deployment using GitHub Actions. But before I talk about GitHub Actions, I think I have to make a quick introduction to DevOps. So, what is DevOps? DevOps is a set of practices and tools that can help our company to improve how we deliver software, and also can help to enhance the collaboration between the software development team and the IT operation team. What are the practices that we can use? A couple of examples are continuous integration to automatically build and test our software, or continuous deployment to automatically deploy our application to specific targets. What are the tools that we can use? First, we need a version control system, and Git is a great option for this scope. Then we need a platform to automate everything, and this is where GitHub Actions comes into play. I have named it a couple of times. What is GitHub? GitHub, I think everyone here already knows what GitHub is. For those of you who don't know it, GitHub is a collaboration platform that can help you to host your code. GitHub provides us with private and public repositories and a bunch of features such as managing work with the issues, milestones, and so on, automation using GitHub Actions, and, for example, also packages to store our libraries somewhere and to make available to other companies or to our clients. Also, GitHub provides us about a couple of features about security. Since the Microsoft acquisition, GitHub has made massive progress regarding the automation part. And this is the topic of this session. This is GitHub Actions. So let's have a look at the platform and let's see how we can automate our deployments. I have prepared for this session 2 different demos. The first demo is a demo written in C# code. So it's the .NET platform. Let me remind you that the .NET platform is a cross-platform, so we can use on multiple platforms, but it is a framework that can target multiple CPU architectures. This is my repository. I have 2 different projects here. This is my GitHub account. These 2 projects are represent a calculator app. The first project is the calculator app project. So I have a class here, which is my calculator class. And then I have another project, which is the test project. And here I'm going to test to check if my calculator works as expected. Now, I want to automate something here. I want to do continuous integration. I want to build and test my software. How can I do that? Here I have the GitHub Actions tab. If I click on it, I have a couple of options to use. As you can see, GitHub suggests me a couple of options. I have the net desktop workflow, and then I have the net workflow. In this case, I will choose the net workflow. So I set up this workflow, and as you can see, GitHub will show me an editor where I can make some changes to this workflow. This is a YAML file, and the file starts usually with a name, the name of my workflow. I can change it if I want. For example, I can name it build and test. And then I have the on section. Here, I will specify which triggers I can use for my to run my workflow. These triggers are based on GitHub events. GitHub has a bunch of events that we can use to automate these actions. As you can see here, I have two different triggers. The first one is a push trigger on the main branch. And then I have a pull request trigger. So each time I create a new pull request that targets the main branch, I will execute, GitHub will execute this action. Then I have the job section. Inside a GitHub action, I can have multiple jobs. For example, build here is a job, and each job can run on a specific agent. In this case, the agent is an Ubuntu agent. These agents are hosted by GitHub, and we can use it. There is a free quota, a free monthly quota that we can use. It's about 2,000 minutes per month. And we have a different option here. We can use Ubuntu, we can use Windows, or we can use Mac OS X. Then we have the step section. Here we have multiple steps, which defines how we want to build and test our software. And as you can see, there is a first step, which is the checkout phase. In this phase, GitHub will clone our repository on the agent, the Ubuntu agent. Then we will prepare the agent to run the build. This is the setup part. And then we have to restore, build, and test our project. But before we see this action running, we have to do a couple of changes. First, if we use our keyboard here, we have the IntelliSense. We have some help provided by GitHub. And here we can define something. In my case, I need a variable to specify which project I want to build and I want to test. So I can create a variable here, which I name a project. And I have to assign the path of the project, which is this one. I can retrieve the path of the project here. This is my project. I can copy and paste it into the variable. Then I have another project, the test project. I can do the same thing here. And I am ready to assign these variables to the .NET commands. The first one is the restore command. I can use that variable using the $sign. So I will put here $project. That's the same for the build step. And then I can use the other variable, test project. to test my software. Now I am ready to save this workflow. I can save it on my repository on a specific branch, or I can create a pull request. But how usually we use a Git repository? If we use GitHub, usually we use GitHub Flow, which is a workflow in which we have one main branch, and when we have to develop a new feature, we create a new branch starting from the main branch. This is a feature branch. We will create all the commits related to our feature. And at the end of the development phase, we will create a pull request. This pull request let know our colleagues that we want to review our code. And usually our colleagues will start commenting the code and suggest what could be improved. At the end of this process, we can choose if we want to deploy our application somewhere, for example, a test environment or even a production environment. So why this is important? Because when I create a new commit here, I can choose if I want to create the commit of the main branch, or I can create a new branch and open a pull request. This is what I usually do. I usually create a CI/CD branch where I store all my workflow files. And as you can see, GitHub will open a new page to create a pull request. When I create a pull request, since there is a trigger that will run my build, the build starts right away. So if I click on details button here, the details link, you can see a real-time log of my workflow. And as you can see, all the steps are executed correctly. And I have built and run and tested my application. So from this moment on, I'm free to deploy my application somewhere and share the code. If I close the pull request, if I merge the pull request, I can share my code with other colleagues. This is a very straightforward example, but since the NDC TechTown is a conference about software and embedded software, I have prepared another example, which is a calculator app as the first one, but this time is written using C++. This is the code of my application. I have a couple of classes. First one, I have an entry point class. Here, the calculator app C++. In here, I will take inputs from user, and then I will check which operation I have to execute. Then I have another class, which is my calculator class. Here, I have a couple of operations that I want to execute for my application. I have another folder, which is the calculator test C++. Here, I have a couple of tests to check if my calculator app works as expected. And here I'm using the Google Test Engine, the Google Test Framework for C++. Now I have my code. I want to understand how can I do continuous integration here. First of all, if I want to build this application, I can use different frameworks. In my case, I decided to use CMake. What is CMake? It's a framework that helps you to compile different programming languages. So in order to use CMake, I have created a couple of CMake lists files. The first one is this one. I have added the project, and then I have added a couple of subdirectories. And inside my folders, I have two more makelist files. The first one is the one related to my application. And as you can see, there is here the project defined. Here I also have a version placeholder because what I want to do during my build and test phase, I want to automatically assign this number using a specific framework. But we will talk more about this later. And then I have a couple of settings related to my application. Specifically here, I have changed the output path for the build phase. Then I have another CMake list, which is related to my tests. This is the configuration of Google Test Engine. And then I have had a single test here, which executes all the tests defined into this file. What can I do to execute these steps? What can I do to build and test my application? First of all, I have to configure CMake. I can do this using CMake option build name of the folder in which I want to store all the build configurations. And as you can see, CMake created for me two different folders. Then I am ready to build my software. And to do that, I can do CMake dot option build, name of the folder of the configuration build configuration folder. Okay, CMake built all my software. This is the calculator app. This is the calculator app test to test my calculator app. And as you can see here in the build output, I can execute now the application. So if I execute the command here, as you can see, there is a welcome message. There is a version number 0 because I have not set it yet. And then I can do some operation here, addition, multiply, and so on. Why these steps are important? Because I want, when I do continuous integration, I have to do the same steps inside my workflow, build workflow. Here, as I said before, I also have the test part. If I go into the build test folder, and then I will execute the calculator app, the calculator tests using ctests. As you can see, my tests are executed correctly. This is the output of ctest and the Google engine test. This is my code. Now, if I want to do continuous integration, I have to do the same steps. So I have another repository here for my application, C++ application. And as you can see, I have already prepared a couple of actions. The first one I want to show you is a workflow related to the build and test part. So I will show you the workflow. This is similar to the one we have seen before. We have a name, we have a couple of triggers. For example, the workflow dispatch trigger will help us to manually run this action. Then we have environment variables. And after that, we have jobs, the jobs section. In the jobs section, I have the build and test job, which will execute the same commands I have just run on my development machine. The first one is the cmake option build name of the folder. Here we have also the configuration, the build configuration. Then I can build my software using cmake option build and the name of the folder. Here we have also the configuration. So what can I do here? I can test using ctest, and then I will execute the application to see if everything works correctly. But this is an optional step. You can also avoid this. In this case, I will run my action on an Ubuntu agent. And as I said before, these are the hosted agent provided by GitHub, and they have a basic configuration, and you can install on this agent what you need to compile or execute your application. In this case, I will install the Google Test Engine, and then I will install a couple of frameworks, specifically Git version framework, which is a framework that can help me to automatically generate the next version number. How Git version works, practically, Git version will take a look at my repository history, and based on the branch I'm in and the tags that are declared on the branch or on the repository, Git version will generate the next version number. I will use this number to change the version of my calculator app. And as you have seen before, this is a line in the CMake list file. Here, I will replace this line with the latest version of my application. Okay, so I'm ready to build and test my software. What I can do here, I can go back to the GitHub Actions tab. I can go in the build and test action. Here I have a button, Run Workflow. I can click on it, and my action will run. Let's give it a second. Okay, the workflow has started. If I click on it, as you can see, I have the log, the entire log of the build and the test executions. This is how I can do continuous integration using CMake and using GitHub Actions. GitHub Action can target multiple frameworks and can use multiple languages, so I can compile my code depending the language I'm using. It's not important. It really depends that the hosted agent that you are using provides that framework. If the agent doesn't provide a specific framework, there is another solution that we'll see later. So my workflow ran correctly, and I have implemented continuous integration for my application. Now, as we have seen before, here we can have a deployment step. To deploy our application, we should first have some devices somewhere in our infrastructure or over the internet. So these devices should be reachable to copy the executable. In this case, I have a couple of devices somewhere, and I will use the hosted agent to build, test, and finally deploy my application to a specific device. I have different options here. First of all, if I want to deploy the application during the pull request phase, I can use different tricks that GitHub provide. I really don't recommend to deploy the application each time a new commit is made on the feature branch. So what I will do, I will use another trigger, which is the pull request labeled trigger. What this means, each time I will put a label on my pull request, and specifically this label, GitHub will start my action. What this action will do? Let's see the editor. So I will go here. Okay, edit. Here we have something similar to what we have seen before, but there is the last step, which is the copy step. In this step, I will use SSH, an SSH connection, to copy my calculator app on a specific device. And in this case, for me, this is an development environment. Here we have a new thing exposed by GitHub. These are secrets. Secrets are variables which contains sensitive information. And these variables are defined in the settings of my repository in the section secrets. As you can see, I have multiple types of secrets. In this case, I have these repository secrets, and each variable will be used in my action. The way I can access to these secrets is by using this syntax. So I have to use this dollar sign with the curly braces. And of course, if I have sensitive information, when GitHub logs all the workflow, the entire workflow, this information is hidden. So how can I execute this workflow? I can go back to my pull request. This is an example of a pull request. When I apply here a new label named dev provisioning, GitHub will execute for me the workflow. And after the completion, I will have here on this device my calculator application. So let's give it a moment to complete the workflow. These are all the steps that we need to build, compile, test, and of course deploy our application. And at the end of all these steps, we can find here a folder which contains our executable, our calculator app. In the meantime, that completes the action. Usually, you can decide to deploy your application after a merge request. And when you do that, you usually have a release pipeline in which you have different stages, and your artifacts, the result of your build, will be passed between the stages. Let's see if the workflow is completed. A couple of more minutes. So this is a very interesting, because using this mechanism, I can easily deploy my application. Let's imagine for a second if one of your colleagues wants to test your new feature. He can simply apply this label, and then he can test on a development stage what are the new features that you have implemented. This is very, very helpful. Okay, this is the step where the copy is done. The action is completed. Then if I check here, I will see this directory. I will go into the directory. As you can see here, I have my calculator app. I can run it. And as you can see, this is the welcome message, but here we have the version number updated. So Git version will generate this number based on the history of my repository, and will assign it using the CMake list file, will assign it here. Let's suppose for a second that we have completed a new feature, and we want to deploy our application first in the QA environment, and then on the production environment. In this case, what we should do? GitHub has an interesting feature, which is the release feature. If you go in the code section, here you can find the release section. And if you open the release section, you can create a new release. When you do that, you have to choose a tag for your application. In this case, I will choose 1.2.0. You can choose the branch, the target branch for your release. And then you can type a release title. Because it's the case, I will use the same version number. You can add some description here. You can also generate a release note, which will contain all the commit messages from your Git repository. When we are ready to publish our release, we can click this button, Publish Release, and a new release is created. So what happens here? I have created another action that will start right after the release creation. If I open this file, as you can see, I have here another type of trigger. And also I have a couple of jobs despite the first one we have already seen. So I have the deploy to QA job, and I have the deploy to production job. These are two more jobs besides the build and test job. What I will do in these jobs? Well, first of all, I have to retrieve my build artifact, the result of my build, and then I have to copy this artifact, my calculator application, on a specific device. This device will be somewhere over the internet, and I have to reach it in some way using SSH. As you can see here, we also have the concept of environment. This job is executed on Ubuntu agent, needs the previous job, but we have introduced another concept, which is the environment concept. What is an environment? An environment is just a logic container related to our environments, physical environments. And we can create a new environment using the environment section in settings. As you can see here, I have two different environments. The QA environment, which I have defined a couple of environment secrets. This is really similar to the secrets you have already seen before. And then I have some protection rules for this environment. I have created another environment for production environment, which is this one. And as you can see here, I have specified one reviewer to approve the deployment on this environment. So what happens here is at the end of the deploy to QA job, before the deployment to production will start, I have to manually approve the deploy. Here I have also other settings, other secrets related to the production environment. Let's go back to our action. So as you can see, I have here the environment QA, and here I have the production environment. All these steps are executed from the hosted agent provided by GitHub, and usually these hosted agents are in the Microsoft Azure data center. So since I have already created a release, let's go back to our release section. Here, we have the 1.2.0 release, and the creation of this release has started a workflow, this workflow here. And this workflow has completed the build and test job and also the deploy to QA job. If I go back to my devices, I can check here if my application has been deployed. So I will check if everything works correctly. Okay, I have here my application. Okay, I need to change the permission here, and then I can execute it. As you can see, the version number related to my application is updated to the latest version number. If I will complete all the tests in this environment, and I'm ready to proceed to the production environment, I can click here on Review Deployment, and then I can approve the deployment. So when I click here to approve and deploy, GitHub will start the deploy to production job, and in a while, in a couple of minutes, on this device, I will have the latest version of my application. And this is interesting because we have a real release pipeline, and we can control how and also when we want to deploy our application. The deployment is completed. Let's check here is everything is okay. Okay, CD apps. I think I have to change the permission here too. Okay. I want to execute my application. Oops. My application is updated to the latest version. Very good. But in some real case scenario, these devices are not accessible from everywhere because usually these devices are inside our infrastructure, and usually they are protected from the external connections. So we can access to our devices only using the local network. And this means that the hosted agent provided by GitHub is not a good option to deploy our applications. What we can do in this case? GitHub will provide us with another runner, with another agent, which is named self-hosted agent. If I go into my settings, and if I click on the action section, there is a runners section. Here you can see that I have an on-premise build runner. I can create a new self-hosted runner using this button here. If I click on it, I can choose which platform I want to target. I want to install this self-hosted agent. And then GitHub provides a couple of scripts, a couple of commands to install the runner. I have already installed the runner on my local network. What I can do here, as you can see, there is an action runner directory. What I can do here, after I have configured my runner, I can execute it, and the runner will connect to GitHub using API, and will check if there is a new action to execute. So we have a couple of files from the GitHub runner, self-hosted runner installation. I have to execute this script, run.sh. The runner is connected to GitHub and is listening for new jobs. And this is important because the connection is from my local network to GitHub. So there are no complications giving access to our infrastructure from external external agents. How I can use this agent and how I can deploy the application on this other on-premise device? I can go back to my repository. Here I have another action, which is named release on-premise environment. And here, let's have a look before at the code of this workflow. The only difference here is the runs on line. As you can see, I will use the self-hosted agent. So GitHub will check for any self-hosted agent installed and related to my repository. And then the steps are all the same. The last step is the copy on the on-premise device of my application. I can execute this action right away. I have here the run workflow button. I will click here on the run workflow. And the workflow will start and will execute the compilation, the build, the tests, and finally will deploy my application on my on-premise environment. Let's give it a moment. Okay, the copy has completed. As you can see here, I have a couple of logs which tell me that there is a job execution succeeded. And then I can check here on my on-premise environment if everything works correctly. Okay, calculator up. And everything works as expected. So this is how we can do continuous integration and continuous deployment using GitHub Actions. I want to add a couple of more things here. First, I want to go back to the editor. If I open a specific action, if I go to the editor, as you can see here, I have the editor, and then on the side I have this pane. This pane can help me to write my workflows. There is a search box. I can use the search box to search something that can help me during the workflow creation. And these actions are provided by community. GitHub also provides lots of action, such as this one, the checkout action. And these are actually Git repository. If we go to the GitHub action repository, as you can see here, we have all the action that GitHub provides to us to integrate into our action. But if you want to create your action, you can do that. You have to create a repository based on a template, and you can then expose your action on the GitHub marketplace. So, for example, if we see this action, I will search for this repository. And as you can see here, this is the repository in which the action is available. And you can use this action clicking here on View or Marketplace, and you can use the latest version using this button. You can find also information related to the action. If we don't find anything that can help us to complete our action, we can use a script, such as a PowerShell or Bash script, and integrate it inside our action. So we have this option. If I go back here and, for example, search for PowerShell, as you can see, I have a couple of actions provided by the community, which I can use to execute scripts into my action. Other things that I want to show you. First of all, if I want to test my action on my development machine, so I don't want to run the action directly on the GitHub interface, I can use a framework named Act. This framework you can install this framework locally, and when you have installed it, it will check the GitHub workflows folder, which is the folder where GitHub will store all our actions. And if we want to execute an action, we can use these commands such as act, option L, and so on. You will find here all the details related to this framework. Another cool feature here in GitHub is the possibility to open an editor, an online editor. If you are into your browser and if you are on your repository in the code section or even on the pull request section, you can press the dot key on your keyboard, and as you can see, the browser will change the page, and GitHub will open for me an online editor based on Visual Studio Code. And in here, I can do multiple things. I can write code, I can make changes. If I'm in a pull request, I can show the differences between the target branch and the feature branch. I can do everything that can be related to my software development. If I want to go back to the repository, I can change here the domain extension, switching from dev to .com. Then, if I want to have an editor and test my application directly into GitHub, I can use another feature, which is CodeSpace. CodeSpace can provide me an environment to build, test, and make changes to my code. This is another very cool feature that we can use in GitHub. So I think I have explained why it's important to automate your deployments. You will have something very reliable to build, test, and of course deploy your application. I will go back for a second to the slides. So first of all, I want to thank you for your attention for this session. I hope the session has been something that you liked. And if you want to have more information, you can scan the QR code here. You will find the demos. You will find the presentation. And you will also find a bunch of links related to what I have talked about. So I want to thank you again. I will check if there is any question for me. I don't see anything here. Let me check on Slido. Okay, I think that's it. So again, thank you. Thank you for your time. If you have any questions, this is my Twitter account. You can shoot me a message. You can shoot me a tweet. And I hope you will enjoy the rest of the conference. Thank you very much. Ciao.
Hello, and welcome to Secure Coding in C and C++, Volatility Ahead. Um, so we're going to spend, I guess, an hour talking about this one keyword, which might not be enough time as things turn out. So um, to keep this sort of relevant with what's going on today, I asked Delphi, should I qualify my variable as volatile? And Delphi says it's good. So apparently it likes the idea. Um, so I'm Robert Secord. I'm a technical director at NDC Group. I spend most of my time doing things like this. I like to develop and deliver secure coding training classes in C, Java, C++, C Sharp. Um, when I'm not doing that, I'll do a lot of code security review for customers, and I'm also the research lead at NCC Group for reducing vulnerabilities at scale and open source software. I'm a expert on the C Standards Committee. I have been since 2004, and actually the first meeting I went to was in Lillehammer there in Norway. So, but that's some time ago now, and unfortunately wasn't able to make the trip this year because of the COVID restrictions. Um, so special thanks also to JF Bastian and Aaron Ballman, who helped me prepare the materials for this class. So here's the agenda. So we're quickly going to touch on some historic context, and then kind of get into the semantics of volatile, and talk about some specific issues following that. So this is a motivating example from way back in the early Unix source code. And you can see here that we have a while loop, and it's trying to iterate until the most significant bit of the keyboard status register mapped to this particular address. You see the number here. Um, is set, and so sorry, the address of the memory map register has become non-zero, and it's a bit of a problem because if the compiler reads this value into a register, then the register value is never going to change because it's waiting for the actual memory address to change. And so this sort of became the compelling reason to add volatility. So if we add volatile keyword, we can now rewrite the loop like this to access that memory through a volatile qualified pointer, or equivalent, we could just declare the pointer object to be volatile qualified, and then access the object through that pointer. And primarily what this does is ensure that that pointer is not cached, and it's actually going to read that memory location on each iteration of the loop. So an object that's volatile qualified can be modified in ways that's basically unknown to the compiler or have other unknown side effects. And so you're basically telling the compiler, that the compiler doesn't know, what's involved with reading or writing from this, and so it should really, perform every read and write that the source code, suggests it should perform. So the volatile keyword imposes restrictions on access and caching. According to the draft, the latest working draft of the C standard, accesses to objects with the use of L values of volatile qualified types are evaluated strictly according to the rules of the abstract machine. So, basically every time there's a read of a volatile qualified type, you have to read it. And every time there's a write, you have to write it. And at each sequence point, the value last stored in the object must agree with that prescribed by the abstract machine. So in the absence of the volatile qualifier, the contents of the location can be assumed to be unchanged, except for any possible aliasing. So then, the compiler can basically, look at things and say, for example, well, I'm writing into this memory, but it's never read from again. So, therefore I don't need to write to it, and I can just optimize that right out. But with volatile, it's not allowed to do that because the act of writing itself might be significant and might have, you know, might have effects that are, side effects that are unknown to the compiler. So you just tell a compiler, you can't, you must do this read or you must do this write. So static volatile objects are appropriate for, say, memory mapped I/O registers, device registers. But the compilers have to take into account the details on the target system about how to implement these volatile objects. So, for an example, you might have hardware that has a 2-byte memory map register, and it can't be accessed with byte operations. So a compiler has to make sure that you never access it with byte operations, even if that's what the source code says. So you actually have to the compiler has to follow the correct rules of the hardware. And so whether or not read, modify, write instructions can be used with these registers also has to be considered, because you're going to both read and write it, and each of those operations might have a side effect. So what constitutes an access to a volatile qualified object is implementation defined, and this is just because the compiler has to, again, sort of understand what the specifics of the hardware register are, and make sort of an appropriate access. Right, it's not always exactly what the source code says. So because it's implementation defined, all implementation defined behavior has to be documented by the implementation. So you should be able to see, exactly what the behavior of that volatile access will be. So a static const volatile object is an appropriate model for a memory mapped input port, such as a real-time clock, where every time you read it, it tells you what time it is. A const volatile object models a variable that can be altered by another process, but not by the current process. And a cast of a non-volatile object to a volatile type has no effect. So if it's a non-volatile object, you can't pretend like it's not a volatile object by trying to cast away the volatility. So to access a non-volatile object using volatile semantics, you need to cast its address to a pointer to volatile and access through that pointer. And we'll talk about that quite a bit more, because there's been a little bit of controversy around that. So we'll have a half dozen slides near the end of the talk to come back and look at that in a little bit more detail. So volatile has a lot of really interesting semantics. So the first of these, again, I kind of mentioned this already, but loads and stores of volatile memory, in the source code have to generate instructions by which each byte is touched exactly once, right? So if there's 4 bytes and I do a write to that storage, all 4 of those bytes have to be written, and only written once. Volatile is used for a variety of purposes. For example, it's used to load and store variables that are used for shared memory signal handling, set jump, long jump, or other external modifications, such as this special hardware support. So the key word here is really external modification. Okay, hello. This is Robert Secord, and I'm going to talk to you today about secure coding in C and C++ and the volatile qualifier. So, just to stay current with what's going on in the world today, I asked Delphi if I should qualify my variables volatile, and it thinks it's a good thing to do. So that's at least the AI position on volatility. Um, so I'm a technical director at NCC Group. I spend most of my time doing things like this, developing and delivering secure coding training classes in Java, C, C++, C Sharp. I also do code security review, code analysis, and I lead the research team at NCC Group that's interested in reducing vulnerabilities at scale and open source software. I'm also a member of the C Standards Committee. I've been on the committee since 2004, and my first meeting was actually there in Norway in Lillehammer. I also wanted to thank JF Bastian, Aaron Ballman, both of whom helped me out with the contents of this presentation. So here's the agenda. We're going to briefly go over some historical context and then talk about volatile semantics, some work to deprecate some aspects of the use of volatile qualified types, talk about inter-thread communication, shared memory, and some updates to the C23 standard. So here's a use case from early Unix sources that sort of motivated the use of volatile in the C language. And here we've got we've got an address specified by this macro KL, and we want to iterate while we're waiting for the sign bit of a keyboard status register mapped to this address in KL to become non-zero. And the problem with this code is the possibility that the compiler might optimize this. So it might read this, memory location into a register and then, just evaluate that register. And at that point, the register is never going to change value. It's only the process of actually reading this address that might produce a new value. So volatile can address this problem and can be used to rewrite the loop where we perform a volatile qualified access to reference the memory. Equivalently, we can declare the low byte to be a pointer to volatile qualified memory and access the byte through low byte. And so the purpose of the volatile qualification here is to prevent the compiler from caching that memory, the value in that memory location into a register. So we want to guarantee that it's actually read on each iteration. So when it finally changes, we can detect the change. Otherwise, we would wind up with a true infinite loop that would never exit. So an object that has volatile qualified type can be modified in ways unknown to the compiler, to the implementation, or have other unknown side effects. So the volatile keyword imposes restrictions on access to that object and caching of the object. So in the latest draft of the C23 standard, it says that accesses to objects through the use of L values or volatile qualified types are evaluated strictly according to the rules of the abstract machine, meaning that basically every read has to be performed and every write has to be performed. So at every sequence point, the value stored, last stored in the object has to agree with what's prescribed by the abstract machine at that time. So in the absence of the volatile qualifier, the contents of the location can be assumed to be unchanged except for aliasing. And so what that means is that the compiler might decide to optimize it, right? So it might decide, well, I'm writing to this storage, but I'm not reading it again, so that's a dead code store, which can be removed. But with the volatile qualifier, it can't be removed because we're telling the compiler that writing to that object might have side effects, and they have to occur. So you have to make sure code is generated to perform that write. So this is appropriate for memory mapped I/O registers. So a static volatile object can be used for a memory mapped I/O register. Compilers have to take into account the relative hardware details on the target system and make sure they implement those correctly when implementing access to these volatile objects. So, for example, the hardware might require that a 2-byte memory mapped register not be accessed with byte operations. You might have to read or write both bytes at the same time. So a compiler would have to assure that no byte operations were generated, even if the source code was only accessing a single byte of the register. So, so whether or not read, modify, write instructions can be used on these devices also has to be considered, right? Because that would both read and write the object in a single, in sequence, and whether or not that makes sense for that register has to be determined. So because of all this, access to volatile qualified objects is implementation defined, right? The compiler has to know, for example, that the particular register maybe has to be accessed, can't be accessed with byte operations. And because this is implementation defined behavior, all these behaviors have to be documented by the implementation, so what they are and how they're performed. So a static const volatile appropriately models a memory mapped input port, such as a real-time clock, right? So you won't write to the clock, but each time you read from the clock, you'll get the current time, for example. A const volatile object can be used to model a variable that can be altered by a different process, but not by the current process. And the cast of a non-volatile object to a volatile type doesn't have any effect whatsoever. You can't cast away the volatility. Sorry, you can't kind of take a non-volatile object and turn it into a volatile object by applying a cast to the object. So to access a non-volatile object using volatile semantics, you can cast its address to a pointer to volatile and access through that pointer. And we'll actually talk about this a bit more towards the end of the presentation today, and what its current status is in the C language. So loads and stores that access volatile memory in the original source code need to generate instructions by which each byte is accessed exactly once, right? It can't be accessed 0 times. It can't be accessed more than once. So volatile can be used, for example, to load and store variables, used for shared memory, for signal handling, and for set and long jump, and other external modifications such as special hardware registers. So the key here is really that volatile is used for things that can be externally modified. So if the source code has a load or store of a volatile operation, these must occur the same number of times in the final execution. So if you have 5 reads and 7 writes, the final execution has to have 5 reads and 7 writes. A volatile operation can't be eliminated or fused with a subsequent one. Even if the compiler thinks it can do it without changing the behavior of the program, just because, again, each write or read is essential. And in fact, if you have volatile qualified object X and you say X equals X, the compiler is required to read X and then take the value it just read and write it back to X. Every read and write needs to be performed. So a volatile operation also cannot be speculated, even if the compiler can undo or make that speculation benign, because the speculation will access the volatile qualified object, and that again can have side effects that the compiler is not aware of. So here's an example of a set jump, long jump program, and in this program we have a variable foo, which we initialize to the value 5, and then we have a set jump point here. And within the set jump, we'll see if foo is not equal to 5, and if it is, we'll print out this string high, and then long jump back to this point here, the set jump point, and retest to see if it's returned 2 or not. And so after this line, we set foo to 6, and then we long jump back here again, but with a value 1. So this isn't going to terminate. It's going to continue through the loop. And so what should happen is that, on the first iteration of the loop, foo is not 5. So we continue executing. We set foo to 6. We jump back, and now foo is 6. It's not 5. So we'll print out high, long jump back to here, and this time we'll exit the loop. But unfortunately, it doesn't quite work like that. So the compiler, of course, is always looking to optimize your code. Typically, that's a good thing. And so what it'll do is it'll look and say, well, for this line, for this code to execute, foo has to be not equal to 5, but it is clearly equal to 5. So the compiler will reach the conclusion that this line of code cannot execute and therefore can be removed. Then it'll look and say, okay, we're assigning a value to foo of 6, but we're not going to read that again. So that's a dead store, and that can also be removed. And the consequence of this is that we now end up with an infinite loop, because we just come down to this long jump with 1 that jumps back to here. It's not equal to 2, so it just iterates for all eternity. So the way this can be fixed is to declare foo to be a volatile qualified object. And what happens now is when the compiler looks at this line, it can no longer say that foo is definitely equal to 5, because we've declared foo to be volatile qualified, and this means it can be changed in a way that's unknown to the compiler. And in this case, this is the change that it doesn't know about, because it's not aware, basically, that this set jump code can be executed multiple times because of the set jump long jump. So by making foo volatile, we prevent this optimization. We prevent this code from being optimized out, and now the code will execute as intended. So for inter-thread communication, volatile object can be used for objects shared among multiple processes. For within a process, most implementations do not insert sufficient memory faces to guarantee that other threads or hardware devices see volatile operations in the order in which they were issued. So it's pretty unclear how to use these weak guarantees in portable code. For volatile objects to be useful for inter-thread communication, updates have to be atomic, as would the reads of those objects. So volatile doesn't guarantee that memory operations won't tear. So a volatile load or read can be observed in could observe partial writes, right? So for example, let's say we were on a 32-bit architecture, and we had a 64-bit value that had to be written or read in 2 instructions, right? So this the high order bits could be written, and then the entire object could be read, and then after it's read, the low order 32 bits could be written, and so we would wind up with a split read where we've got half of the new value and half of the old value, right? And that would not be good. So we had to be concerned about volatile reads and writes being split, being ripped. So realistically, the only reads and writes that will tear is when the hardware doesn't have an instruction that will perform the entire memory operation atomically. So if you have a type like SIG-atomic T, that's guaranteed to be readable and writable atomically. But for larger types, there might not, like the previous example of our 64-bit object on a 32-bit architecture, there might not be an instruction that can read and write the entire object at one time. So an implementation is required to touch each target byte once, one after the other in an unspecified order. And that order could change on each execution. The order of volatile operations cannot change relative to other volatile operations, but it can be reordered relative to non-volatile operations. So volatile doesn't imply any observable ordering in the memory model. Atomic instructions will guarantee sequential consistency for data race-free programs. If you have a data race, data races are undefined behavior, and once you have undefined behavior, basically anything can happen. There are no guarantees anymore. So volatile doesn't provide such a guarantee and doesn't imply a memory ordering or any fencing, although there are some implementations such as extensive processors and Microsoft Visual Studio that will provide stronger guarantees. So the instructions are emitted in a defined order, but processors can issue and execute them out of order, and other cores can observe them completely different order if there's no extra synchronization being used. So this will come from, or can come from, implementation guarantees or hardware mapping specifics. So here's an example of the use of volatile for synchronization, which of course is something that you shouldn't do. So in this example, we have a volatile qualified Boolean called G update finished, and we've got a thread. So we've got our first thread that initializes this volatile Boolean flag to false. And then we perform an update of some global data, and then we perform update of some other global data. And once all our updates are finished, we set this volatile Boolean flag to true. Then the second thread is basically looping, waiting for this flag to get set to true, so it knows that these updates have completed, and now it can go ahead and render, the global data. And the problem with this code is that, again, reads and writes of volatile qualified objects can be reordered with respect to non-volatile operations, and so the compiler, is free to relocate this code to before these global variables are actually updated. So the second thread could detect update finish being set to true and decide that these variables have been updated and render them when really they haven't been updated yet, or maybe are partially updated. So again, you don't want to use volatile for synchronization. It's not designed for this purpose. It can be a bit confusing because in Java, volatile can be used for synchronization because they have a different memory model, but in C and C++, it cannot. So basically, volatile is used for external modification. So examples include shared memory, where volatile can avoid time of check, time of use, or toctale race conditions, which can pretty easily result in software vulnerabilities. Signal handling is another use case where signal can occur at any time in the program's execution. And the optimizer has to ensure that the volatile operations occur even if they are allowed to tear. It's used, as we've already seen in a prior example, in set jump long jump, where set jump can effectively return twice. So volatile will be used to prevent the motion of memory operations around that operation. And external modifications such as memory mapped registers, where the compiler can't assume the memory hasn't changed, or any write to that memory isn't having some sort of side effect. So in C++, but not in C, volatile can also be used to mark an infinite loop that has side effects and is therefore not undefined behavior. And finally, it can enforce control dependencies and prevent compiler value speculation. So as we kind of pointed out already, volatile has implementation defined behavior. So the C standard says that an assignment expression has the value of the left operand after the assignment, but is not an L value. The implementation is permitted to read the object to determine the value, but is not required to, even when the object has volatile qualified type. So what you're getting here is some flexibility where the compiler has the option, but is not required to read the value. So the consequence of that is that this code has implementation defined behavior where A and C are not volatile qualified objects, but B is a volatile qualified object. So we're going to assign, the value in C to the location stored by B, and then we're going to assign a value to A, right? But it's unclear if we're going to read B again in order to assign it, or we're just going to assign it a second time into A. And so there's two independent but valid interpretations of this, both of which access the volatile qualified objects in different ways. And so that's quite problematic, right? Because accesses of these volatile qualified objects could could have a meaning, and you want to be very precise in determining how many reads and writes occur and in what order. So basically, this has become a deprecated behavior in C++, and we've proposed also to deprecate it in C. But it's a good idea. Whether or not it's deprecated, you want to avoid that type of code. So if what you're trying to do is you want B to be read after being written to, then it's best to write the code out like this to make it clear that we're going to put the value in C into B, we're going to read B, and then we're going to write that value to A. So this will get you a write followed by a read of the volatile qualified object. On the other hand, if we don't want to read B, we can just assign C to B and then assign C to A. And this will indicate that we don't want B to be read. So this is clear and unambiguous, while this version of the same code is not unambiguous. Okay. So again, this behavior has been deprecated in C++20, and I've written a proposal to deprecate it in C, but the committee hasn't heard the proposal yet, so we're not sure what the outcome of that will be. But this is currently deprecated behavior for C++20, and we'll see what happens for C23. But regardless of what decision is made, right? You want to avoid writing this code because it's clearly ambiguous and could be wrong. So another issue is with compound assignment. So here we've got a structure describing a device, a controller, and we want to either to start the device or we want to stop the device. And so the way we start the device is that we OR this address with this value and then assign it back to the address. And to stop it, we AND the complement with this value and store it back in the value. And what's a little bit, unclear about this logic, and here we've put it in, say, a header file that might be included into a C or C++ program, is the fact that these compound assignments. So the compound assignment of that form, it basically is equivalent to E1 equals E1, and then whatever operation is E2. Except that it guarantees the value E1 is evaluated only once when you use the compound assignment. But this operation is still a read, modify, write operation. So basically, this value in a controller is going to be read and then modified. We're going to OR it, and then it's going to be written. So we're going to have two accesses of this volatile qualified memory, first to read it and then write it. And it's not always clear, looking at code with these compound instructions, that there's going to be multiple accesses of that volatile qualified storage. The same thing is true of pre and post increment and decrement of volatile qualified types. It's a read, modify, write operation. So if I say, I++, the first thing that happens is we have to read the current value in I, then we have to operate on it or modify it by incrementing it, and then we have to write back the value into I. So the object again might be will be accessed more than one time. So C++20 deprecates this, and we have our proposal in C to make this obsolete for a volatile compound assignment, and for pre and post increment and decrement operations to be performed on volatile qualified objects. Okay, so shared memory. So here's an example from Chromium where basically we have a GPU process here, and we've got a rendering process here. So there are multiple processes, and the rendering process is going to send WebGL commands to the GPU to execute. And the way it works is that you call a function, and that function will write the command and the arguments into a command buffer, and the GPU process will loop and read these commands from the buffer and then process them. And when it's done, it'll actually then write a result back into shared memory to communicate it back to the rendering process. So there was a CVE for the software with the unlikely number of 1, 2, 3, 4. And so this was in this command decoder which allowed remote attackers to cause a buffer overflow. And what was happening was that the GL get uniform FB API, OpenGL API was being called. The shared arguments, the shared memory used for the commands is going to be filled with the appropriate function ID and the arguments to that function. The GPU would then read the command and process the data, and then write the return value back into shared memory for the rendering process or the client process. So the vulnerability in this case is triggered by having these two threads running, and one thread, kind of the attacking thread, would continuously call GL get uniform FV, while the other one is going to process the commands and write to the value where the result resides, and the result in this case is a size. So the way this was fixed was with this with this code here. Size result here is just a struct with pod members, and this call here to get shared memory as is just going to return the pointer to shared memory. And so the key to this is really, here's the right, the shared memory store, but this was causing the race condition because this size could wind up changing again before it was used, and then because the GPU had an invalid value because it was changed because of this, basically this TechTown condition, it would wind up with a buffer overflow because it no longer knew the size of the object it was writing to. So the way this was fixed was that the size value is also it is stored into shared memory, but it's also stored on the local stack where it can't be overwritten. But the problem with this solution is that the compiler doesn't know that this shared memory can be externally modified. And consequently, it can perform a lot of optimizations around this, such as delaying the store indefinitely, reusing the stored value, not using result size, or even reusing result size as temporary storage. Because as far as the compiler implementation knows, this memory is not shared with anyone, and no one else is accessing it. So in order to let the compiler know that this is shared memory, you can declare it as volatile, and then it now knows that this can be modified in ways unknown to the compiler. So volatile atomic, as we've already seen, volatile can tear. It provides no ordering guarantees with respect to non-volatile memory operations, and also with respect to CPU reordering. It's required to touch bytes exactly once, and it inhibits optimizations, which is the purpose it serves. Atomic, on the other hand, cannot tear because all the operations are atomic. I can't think of another word for that. Maybe there is one, but so these operations cannot tear. It has a full memory model, but it can require a loop to succeed, and it can be optimized. So ideally, you would think that by combining these two together, you would get the union of properties, but this is not true. So, for example, read, modify, write operations can be implemented by loops, which are going to retry with locked instructions, each of which performs a load and store. So the fact that you have a loop where you might retry multiple times, loading and storing these objects, means that we've lost the guarantee with volatile that these bytes are going to be touched exactly once. Similarly, we could implement this with transactional memory operations, which might also access the bytes multiple times. The only way really to ensure that you're only touching the byte once is to do these as memory controller operations. So, so if you want to, so a non-lock-free atomic can be volatile, in which case it can tear when you consider the instructions that might be generated. So here we're going to look at a little example where we have a volatile atomic object, which is a small int, which can be which has a lock-free atomic, and we've got a larger struct which contains a 16 element integer array, which which doesn't have a lock-free atomic associated with it. And so if we look first at the larger object and we attempt to make a copy of it, you'll see that there's a bunch of instructions that need to be called. So the problem is that, you know, a volatile atomic operation needs to be performed as a single copy atomic across shared memory when the processes can't share a lock. Without this, without having the lock-free atomic, you're going to end up with just a regular unprotected memcopy. So this is not what we want. On the other hand, if we have a lock-free atomic, for example, of this integer, this you know, we're now assured that this lock-free atomic instruction can't rip, and so you know, to get this volatile atomic behavior, you really need to have lock-free atomics for this to work successfully. Okay, so I mentioned earlier some wording changes in C23. One of the problems with volatile, when you read the current version of the standard, which is C17 or earlier versions of the standard, is that volatile semantics are specified to apply to objects declared with the volatile qualifier. So the standard says, for example, accessing a volatile object, modifying an object, are side effects, which are changes in the state of the execution environment, and that accesses to volatile objects are evaluated strictly according to the rules of the abstract machine. So the C standard refers to volatile objects as regions of storage, storing the representations of their values. And so you can see here that, you know, volatile is associated with the object, you know, with the storage of the object, with the data. So, so objects are distinct from the expressions that are used to designate and access them, right? So those expressions are called L values. You know, it's basically an expression that when evaluated is going to reference a particular object. But it doesn't have to mention the name of the access object. It could just be, you know, accessed through a pointer. So if we go back to the original example that we had for, you know, the motivating example in the early Unix source code for introducing volatile, you know, we had KL, which was an address in memory, and so there's no way to declare that volatile. So instead, there was an expression where we, you know, we cast it to a volatile qualified pointer and then access it. So the object itself is not a volatile qualified object. It's just being accessed through a volatile qualified L value. So L values are not mentioned by C17. So volatile semantics could be inferred to not apply to these accesses. And you know, it's definitely, you know, a legitimate reading of the standard, although you know, the response to this is, well, this is exactly the reason why these were introduced. So in the Linux kernel, relies on volatile in its implementation of synchronization primitives such as spin locks and performance counters. So the objects that are operated on by these primitives are usually declared to be unqualified or non-volatile scalar types and just allocated in ordinary memory. So this is for maximum efficiency, so that each object is read and written just like any other object, and so the value can be cached in a register, and various optimizations be performed. So at well-defined points in the kernel, a variable might need to be accessed by more than one CPU at a time, at which time we want to prevent caching. And so on these occasions, these objects need to be accessed through the volatile semantics. So to achieve this, the kernel has two macros, a read once and a write once macro, which basically provides these primitives using volatile semantics. So each macro prevents the compiler optimization by casting the argument to a volatile qualified pointer. So Linus Torvald weighs in on this by saying, volatile is on the wrong part of the system, and see, it's the data that's volatile, but that's insane. Data isn't volatile, accesses to data are volatile. So it makes sense to say this particular access, be careful, but not make all access to this data use some random shit. I'm not sure it's random, but basically be treated as a volatile qualified object. So that's correct, and this was I think the original intent of this all along. It's just that the language in the C standard wasn't very clear. So in C23, we've already modified this language, and this will be found in the latest working draft of C23. And so basically, what we've done is we've taken every reference to volatile object that appeared in the standard and replaced it with language which says, access through an L value of a volatile qualified type, right? So basically, we changed the language in C23, so it's no longer referring to the data, the volatile qualified object, but instead is referring to the access through a volatile qualified L value. So this really should just be a wording change, and it's really designed to make sure the language is in line with what we hope all existing implementations are already doing. So hopefully there are no implementations that actually have to change to satisfy this new language. So in summary, volatility is on the access, not on the object. Well, it can also be on the object, in which case all accesses would have to be volatile, but the access itself can be volatile even if the object is not volatile qualified. There are a number of misleading or invalid volatile operations that we've seen, including the simple assignment, compound assignment, and pre and post increment and decrement operations. These have been deprecated in C++20, along with some other uses of volatile that are unique to C++, but may or may not be deprecated in C. That's still to be determined by the committee. But it's a good idea to avoid these deprecated operations in both languages, for security reasons, because the sort of uses that we've described are prone to misuse, and so you could wind up with a defect or a security vulnerability quite easily. And also to maintain compatibility between these languages, because C++ has deprecated this behavior, whether or not C does it. So you want to avoid the deprecated behavior again in both languages. So volatility does not prevent tears, and atomicity doesn't guarantee bytes are only touched once. Volatility overall is about external modifications. It's not about anything else, particularly about synchronization. So volatility preserves the order of memory operations relative to only relative to other volatile operations. So again, it's not generally suitable for thread synchronization. You want to use other synchronization primitives instead. So here's a list of references to various papers. This is the C proposal that the C committee is going to review. Here's various versions of J.F. Bastian's proposal to the C++ committee. Eventually, it was the R4 version, which was adopted, and some additional papers that provide some background material for this talk and for these other papers. So that's it. That's all I have to say about volatile. If you have any follow-on questions, you can find me on Twitter at RCS. You can find me on LinkedIn. You can send me email. You can call me, but I'm not really good at picking up my phone, so that's probably the worst of the options. But anything else, I monitor pretty regularly, so you should hear back from me pretty quickly. So if there are no other questions, I'm going to end there, and thank you for your time.